Hello students, so let's try to solve one more problem from JEST 2022, and this is a problem from quantum mechanics, and this is all about Pauli exclusion principle. So it is given the potential is a three-dimensional harmonic oscillator that Vx is equal to 1 by 2 m omega square x square plus y square plus z square. And what we have to do, we have to just adjust the 5 spin half particle. And if we are going to adjust the 5 spin half particle, then we have to calculate the degeneracy of a system or degeneracy of a ground state, basically. So degeneracy for the ground state we have to calculate for this particular system. So it's a quite conceptual question. So let's go for a step by step. So for the three-dimensional harmonic oscillator, the energy is given as n plus 3 by 2 h cut omega. And where this n is given by 0, 1, 2, 3, and so on. But this n is actually nx plus ny plus nz, and this nx, ny, nz are the three quantum number associated for x degree of freedom, y degree of freedom, and z degree of freedom. And they are basically nx is equal to separately 0, 1, 2, 3, ny is equal to 0, 1, 2, 3, and nz is equal to also 0, 1, 2, 3. And for the Pauli exclusion principle, in one particular quantum state, only one particle can be adjusted. And we have talking about the 5 identical spin half particle. So each energy state can have two possible extra quantum states. So let me explain you what I am trying to say. So if I am talking about n is equal to 0, and this energy eigenvalue is 3 by 2 h cut omega. What is meaning of that? N is equal to 0. We have only one state, that is nx is equal to 0, ny is equal to 0, and nz is equal to 0. So why n is equal to 0? And after then, if we are including the spin, then we have two more quantum state is going to associate here. So this is the status if we are going to include the spin half and the spin minus half in this particular picture. So similarly, for n is equal to 1, the energy eigenvalue is 5 by 2 h cut omega. And here, n is equal to 1 can have 3 different levels. So if we are talking about 3 different levels, all have same energy, and these can be just represented as nx is equal to 1, 0, 0. Second can be 0, 1, 0. And third can be 0, 0, 1. And this is the combination of nx, ny, nz. Now, if we are going to include the spin, then this can be further divided into two states. This can be further divided into two states. This can be further divided into two states. So, and next we can go for next level and so on. Now, if we have 5 fermions of spin half, so 5 fermions. So first 2 fermion will adjust into this particular level, and then rest of go into the higher level. So if 2 fermion is going to this level, there are number of ways that 2c2 is the number of ways. So only one way that 2 fermions can be adjusted. So because in every state there is only one state is possible, and these fermions are indistinguishable. So you cannot say this is my first fermion and this is my second fermion. So you cannot say. So why we have 2c2 is there. Now rest of 3 fermions have to adjusted into this 6 quantum state. So this 6 and this can be filled by 6c3 way. So the total number of way is equal to 2c2 into 6 C3 way, and that value is 20. So if you will calculate, this is 1 and this value is 20. So there is 20 different way such that we can adjust the particle. If this is 20 different way, that means we can write 20 different energy eigenstate with the different quantum numbers. So we can have 20 different energy eigenstate that can be represented for the ground state energy. And what will be the ground state energy? If you will ask for the ground state energy, then this will be 2 into 3 by 2 h cut omega plus 3 into 5 by 2 h cut omega. And this energy eigenvalue I have calculated, that value is 21 by 2 h cut omega. So if we want to find 21 by 2 h cut omega for this particular potential, that will be the ground state energy. If we are filling the 5 fermions of a spin half particle with a spin half, then there are 20 different energy eigenstate can be possible. So this is wonderful problem. The permutation combination is there. And most important thing is that we have to identify fermions are indistinguishable. So you cannot say this is my first fermion, this is my second fermions. So either you have fermion with half or minus half. So all this concept is coming into this particular problem. So if you want to revise the Pauli exclusion principle, then this problem is awesome and you have to go through this problem. What is Pauli exclusion principle? In every quantum state, there is only one fermions can be adjusted. This is the gist of this particular problem. Thank you.